Hello and welcome to the 6.2 notes. This is a section about areas between curves. We've just been calculating areas under the curve, but now we can actually calculate areas between curves. So the first thing I want to do is talk a little bit about just some notation. And I want to just quickly draw a graph. And so I just want to draw a generic graph here from, say, a to b and some function like this, and we would calculate the area between under this curve. Okay, so we have this area here that we want to calculate, and our area, remember, is equal to the integral from a to b of f of x dx. Okay, and when we do this, what I always like to do is to draw a tiny, tiny little rectangle. Because remember, what we're trying to do is we're trying to, when we have something like this, that means we're adding up an infinite number of rectangles in here. So the thickness of this rectangle, we're going to call that dx, okay? And the height of that rectangle is the function value, f of x, okay? And so when I multiply f of x and dx, this is just the height of the rectangle, and this is the width, okay? And this is going to help us when we're trying to figure out how to set up these integrals, and it'll help us when we further on in this lesson. So the first thing I want to do is talk about vertical distance. Okay, so vertical distance. And so, what I like to think about is, I'm going to give you two different examples. If I've got, say, a vertical distance, let's say I have a number line here, a vertical number line. Let's say that this is 0, and this is 1, and this is 4. Or not 4, let's say this is 5. Okay, and what we know, if I'm trying to find the distance between 5 and 1, this distance is a distance of 4. Okay, and it's easily calculated just by kind of looking at it. We just kind of know. But there is some math involved, okay? And, let's say that you had this. Let's say that you had a number line where you had, say, instead of 5, it was 5.387, and say the number 1.732. Okay, finding the distance between these 2 points is a little bit different. Okay, and so I have to think about something like this where you go, okay, well, how do I calculate? How do I use the numbers 5 and 1 to get 4? And, the trick is we'd want to subtract, 5 minus 1. Okay, that's the idea. And so same thing here. If I wanted to calculate the distance between those 2 points, I would take 5.387 minus 1.732. Okay, and so one of the things we need to, one of the ways I can remember this, if I'm trying to find a vertical distance, that means I want to do top minus bottom, okay? And that's kind of the big thing. That's what we got to remember when we're talking about areas between curves. And then, what if you had a negative number? What if your number line, went from, say, positive 7, here's 0, and then here's negative 3. Okay, even calculating the distance between those 2 points, we would still subtract. Okay, we know that the distance between them is 10, but, if I took 7 minus negative 3, that's really going to be 7 plus 3, which gives me 10. Okay, so top minus bottom, that's what we really need to remember here. That's the important thing. And I am going to go ahead down here. This little definition here tells you, what you would do, and it says here that, this function f is larger than this function g. And so if you were to calculate the area between two curves, you would take f of x minus g of x and integrate between a and b. So, but I do want to reiterate that this is our top function, okay? This is top, and this is our bottom function. So top minus bottom, okay? So let's go ahead and take a look at example 1. I've gone ahead and graphed this for you. And what we want to do is we want to find the area of the region bounded by the graph of f of x is equal to 5 minus x squared. And that's this graph up here, okay? Y-intercept of 5, and then the graph x squared minus 3, this graph down here. So I'm going to go ahead and call this graph, you know, f of x, and then this graph down here, I'm going to call this g of x, okay? Now, the other thing that we need to talk about is where do we start and where do we end, okay? So I want to write this out, that our area is equal to the integral from -2 to 2, all right? And, you know, there are algebraic ways to calculate this. Right now, we are just concerned about setting up these integrals. We'll go in further on how to calculate these, especially if you don't have a graph or you don't have a calculator. But for right now, we're just interested in you setting these up. So the next thing I want to do is I'm going to draw a slice. Okay, I'm going to draw a tiny little rectangle, a very thin rectangle, from the top of my function to the bottom. Okay, and so the thickness of this, I'm going to call that dx. And I'm going to do this every single time, just so I know what variable we're using. We will be able to use other variables. And so, you know, the idea, remember, is that I have a rectangle at every single point here. And all of these rectangles are different sizes, okay? And depending on whatever x value we're using, we can calculate the heights simply by subtracting the top number minus the bottom number. But since we're dealing with a function here, okay, you know, over an interval from -2 to 2, you know, we have to be generic here, and we have to talk about just subtracting one function, the top function, from our bottom function, okay? And so, you know, what I want to do is our top function is just 5 minus x squared. So I'm going to write that here. So I would integrate from -2 to 2 of 5 minus x squared, okay? And then I'm going to subtract the entire function of x squared minus 3, okay? And so, and then I'm going to put dx here, okay? So this is the top part, okay? This function right here is my top function, and this over here is my bottom function, okay? And so then we want to clean this up. We want to do, you know, manipulate this so that we don't have so many parts. We want to combine like terms. And so our area, you know, is going to be the integral from -2 to 2. And I'm going to go ahead and just distribute my negative here. And so I get 5 minus x squared minus x squared and then plus 3 dx. And then I'm going to simplify this, and I'm going to get area is equal to the integral from -2 to 2 of 5 plus 3 gives me 8, and then minus 2x squared, okay, dx. Now, this is what I want to evaluate in the calculator, okay? You can do this one by hand, obviously, and the answer of what we would get, the area here, by putting it in our calculator, would be 64/3, okay? So, you know, and all I want to do is to be able to set this up, okay? So let's go ahead and take a look at a second example. And in this example, we have what's called a compound region, okay? And so, you know, we have this function f of x here, which is x plus 3. That's this linear function here. And then we have g of x is equal to the absolute value of 2x. And that's this v function here. Now, what I want to do is let's go ahead and define what g of x really is. I'm going to put it as a piecewise function. G of x equals the absolute value of 2x, and that's equal to, you know, on this portion of the graph, this is the function -2x, okay? So I'm going to write this piecewise function here that I have -2x, and then at 0, we switch and we have positive 2x. okay? And so now, and let me just write out that this exists when x is, say, less than 0, and this exists when x is greater than or equal to 0, okay? So what I want to do here is I'm going to label this over here as this is the function negative 2x, and this is the function positive 2x, and then this is the function x plus 3, okay? So, you know, here's the thing, and here's what I want you to see, is that the thing that I do here, the first thing I do is I draw my slice. And I'm going to draw a slice going from the top function to the bottom function, okay? My width is the change in x, so that's dx. Now, what I notice here is that in between negative 1 and 0, I'm going from x plus 3 down to negative 2x, okay? But then all of a sudden, at 0, I switch, and if I draw a slice over here, then I'm going from this top function, x plus 3, down to just 2x. So what I have here is I have really just two different areas. I have this area that I can calculate, and I have this area that I can calculate. So let's do the part over here, okay? And so if I wanted to calculate this first area, here's just an area, I would integrate from this point of intersection from negative 1 to 0, because at 0 things change, okay? I switch to a different function. So I'm going to write this as the integral from negative 1 to 0 of my top function, which is x plus 3, okay, and then minus my bottom function, which is negative 2x dx, okay? And now, you know, because I have that, you know, just this one area, I need another area for this. So I'm going to write this as plus another integral from 0 to the point of intersection, which is a 3. So from 0 to 3 of my top function here, which is x plus 3, minus my bottom function, which is 2x. So I'm going to write x plus 3 and then minus the function 2x and then dx. Okay, I'm going to make this black. Okay, so so if I you know, want to, I can simplify each of these integrals. Okay, I can do this one separate and then this one. So I have my area is equal to the integral from negative 1 to 0. And this becomes x plus 3 plus 2x dx, okay, plus the integral from 0 to 3 of, okay, x minus 2x is really just a negative x, so I get negative x and then plus 3 dx. And now I can combine my like terms on my first one. So I've got the area is equal to the integral from negative 1 to 0. And this gives me 3x plus 3 dx, and then plus the integral from 0 to 3, which is just negative x plus 3 dx. Okay, and this will represent the area between those two functions, okay? And so our area then is just going to be equal to 6. But that's, you know, after you did this by hand or putting it into the calculator, okay? I'm really just concerned about you setting these up, okay? We've already gone over how to integrate all this stuff and all that. So I hope you've enjoyed this video. You know, this is some brand new stuff, but it's really powerful stuff, and we'll be able to use it, from here on out. So stay tuned. We got another video to go, and we'll see you in a bit. Thanks. Bye.